All right, our last section of material, we learned how to expand and condense logs. And when we talked in that section, I mentioned that sort of the end result where that was leading up to is being able to use those properties in order to solve equations. And that's what we're taking a look at today, is solving equations, both logarithmic ones, which we've been most directly working with, and exponential ones, which we were working with earlier. So literally, we're just going to do a whole bunch of examples, all right? Some of them have different sort of flares to them. There's a reason that I chose each of the types I did. They are uniquely different, each of them. This first one, what you'll see is you have a single log on one side, and you don't have a log on the other side, okay? So anytime you have a single log on one side, and you don't have a log on the other side, it'll look a lot like this problem. Now, do you remember when we were working very early on with logarithms and I showed you how we could move them in and out of the log notation, from logs to exponentials to logs? That's what we're going to do on this problem. So we're going to use that scorpion tail notation to turn this into an exponential. So I start with my base, which is a 5, cross to the other side of the equation, which I would get a power then of 2, and it will equal where I land, which is 2x minus 4. That step okay for everybody? Because we've got to be able to get that step before we can do anything else. Okay, great. What is 5 squared? 25. What would I do next? Yeah, I'd add 4. What's 25 plus 4? 29. And then what would I do? Divide by 2. So you can leave it as 29 over 2. If that super bothers you, you're welcome to change it. It would actually be 14.5. Decimals, fractions, doesn't really matter. Throughout this problem, if we do end up with something that we need to round, we're going to round to the hundredths place. Some of the problems say hundreds, some of them say thousands, so just for the purpose of our discussion in class today, I just decided we'd go with hundredths, okay? All right, any questions on that one? So that's how it is if I have one log on one side and nothing on the other side, like no log on the other side. How does this problem look different than the last one? There's a 5 over on the same side with the log. But what do you think I could do to make it look like the last problem? Right. I just need to subtract the 5 from the 9 to begin with. And then I've got log base 2 of negative 5x equals 4. And this problem now looks like the last problem. So I'd like for you to finish it from here, and we'll make sure that you're on the same track as I am. Okay, when you have an answer, compare with a neighbor. See if you got the same fraction or decimal. It is one of the two. Okay, what answer are you guys getting? Negative 3.2. Awesome. Okay, so let's make sure everybody has the same work. You start with the base of 2 and draw your scorpion tail, right? So I have 2 to the 4 equals negative 5x. Does everybody have that step? Awesome. Did you know what 2 to the 4th was? 16? Excellent. 2 to the 4th would be 2 times 2 times 2, 4 times, right? So we get 16. Very nice. And then if I divide by negative 5, again, you can leave it as negative 16 over 5. If that bothers you, another way to write that would be negative 3.2. Good job. So, again, all I really did was turn it into something that looked like a problem I already did, right? So how does problem 3 look different? There are 2 logs. They're natural logs as well. We'll deal with the fact that it's natural logs in a minute. But there's 2 logs on the same side. Is there any way I could change it so that I don't have 2 logs, but instead I have 1 log? I can use the combining rules from the last section. Good job, guys. So, how would I combine these 2 logs because there is a subtraction sign here between them? I would divide. Now make sure you're dividing the inside of the logs, not dividing logs. So the inside of my 2 logs are x plus 2 and 2. And then this will equal a 2 when I'm done. Okay, now we're going to go back to the fact that Keely noted that it's actually natural logs as well, which makes it a little bit different, right? There's not a number written down there as a subscript, notationally. But what is the number that's there? It's not a 10, but it's an e. If it were just plain log, we're going to get to one that's just plain log here in a minute, it will be 10. But this is actually natural log, so it's an e. So this is equivalent to having log base e of x plus 2 over 2 equals to 2. And then I can do the same thing I did on the previous problems. I circle my base and draw my tail. So this says e squared equals x plus 2 over 2. Now we talked about before that e is just a number. It's about 2.718, and it's in your calculator with far more decimals of accuracy than 3. We need to actually get a decimal approximation to work with this. So go ahead and take your calculator and have it do e squared. Okay, if you can't find your e, flag me and I'll come help you find where your e is, or if you're not sure how to square it. So as long as we're working with e's, you're going to need a calculator for this homework assignment, and it will be on there, okay? In the end, our answer needs to have 2 decimals, so while we work our way through, we need to at least keep 3 so that we don't lose accuracy. You guys have been working in chemistry. You can lose accuracy pretty quick in problems, right? So we're going to keep at least 3 for now. So with 3 decimals, what is e squared? All right, 7.389, good. All right, so I now have 7.389 equals x plus 2 over 2. What would you like to do next? Multiply by 2 would be great. So it'll cancel out on the left, or on the right, excuse me. And if you take your 7.389 times 2, what do you get? 14.778, and that's equal to x plus 2. And then what? Subtract 2. So now is where I'm going to write the answer to 2 decimals instead of 3, because I'm at the point where I have my final answer. What does x equal? 12.78. Good. All right, so we're going to go back to the 3 problems that we've already done, and I want you to make notice of one thing. We haven't had it come up yet, and I can't actually remember if it does in my examples that I picked, but it might in your homework. We need to make sure that whatever answers we get, they don't give us inputs inside of logs that are negative. Because that sometimes happens when you start doing algebra and you shift things around, is that you introduce numbers that aren't really solutions. They solved something else that was almost equivalent. So we just want to make sure that as we did these, we didn't end up getting answers that make the insides of logs negative. So this one was 14.5. If I multiply 14.5 by 2 and I subtract 4, do I still have a positive number? Yeah, I do. How about the negative 3.2? Here's the inside of my log, right? Negative 3.2 times the negative 5 would give me a positive, so we're good to go on that one. And then the 12.78 on this one, plus 2, also positive, right? Okay, so we're checking as we go along. All right, how is this one different than the one we did before? There's 2 logs, but they are on opposite sides. So what should I do? Get them on the same side and then combine them. Right, so it doesn't matter which direction we move it, but since we've already got the one on the right-hand side, we might as well move the logs to the left. So this is log base 4 of x plus 2 minus log base 4 of x plus 5 equals 1. Then how would I combine my logs? With division, good. I would divide them. X plus 2 over x plus 5. What's next? Do a scorpion tail. All right, so how will this be rewritten with my scorpion tail? Very nice. What is 4 with an exponent of 1? It's just 4. So what would I do now? Awesome. I'm going to multiply by x plus 5. So of course I do that because it's going to cancel on the right. What is x plus 5 times 4? 4x plus 20 equals x plus 2. Now what? Subtract an x. So I have 3x plus 20 equals 2. And subtract 20. So 3x equals what? Negative 18. My problem was different in my notes, but this is actually good. I'm glad this came about. Okay, good. And then what's the last step? Yeah, x equals negative 6. Cool. Or is it? Does x really equal negative 6? What's wrong with that? Why am I acting this way?
It doesn't check in.
Yeah, if I go up to my original problem and I try to put a negative 6 in actually either one of those logs, I'll get a negative inside it, correct? So that's no good. And the reason that happened was because when I combined two negatives together, what's a negative divided by a negative? A positive. So those properties of logs sort of masked the algebra that was going on, and it yielded a solution that doesn't actually really work. So what do you do when you get to the end and the solution doesn't exactly work, right? Well, you mark it out and you say no solution. There's a name for a solution that comes about that's like that. It's called extraneous. I can't remember if I've told you that word before or not, but extraneous means that it's a solution that the algebra yielded, but it doesn't actually work in the original problem that you were starting with. All right. How is this problem different? There's 3 logs, but not only is there 3 logs, but there's also no constants. Do you see how every term is a log in this one? Okay, so that's actually super friendly. So let me show you why. We can combine the 2 logs that are on the left, correct? How would we combine those? With multiplication. Cool. So I've got log 3 times x minus 7 equals log x. If I can write both sides of the equation so that they match, they both say log, like this, right? Then the only way that they're going to actually be equal is if the insides of the logs are equal. So I'm not dividing by log. That's like saying, can I divide by a square root? Well, no. I mean, that's an operation. Can I divide by multiplication? Well, no, it's an operation, right? I'm not dividing by log. But what I am saying is that the log doesn't matter because they match. So what I really need to know is where the insides are equal. So the problem actually becomes this. I need to set the insides now equal to each other and solve. I didn't even have to use a scorpion tail for it. So I can simplify this. 3x minus 21 equals x. I can subtract my 3x. So negative 21 equals negative 2x. Divide by negative 2, and what is x? Yeah, 21 halves or 10.5. Whichever you like. And is that okay within the problem that we started with? Yeah, that one gives me positive answers, so that one's good. Okay, that's all the varieties of logs, that is log equations. So the other half of the instructions, or the title of this section, if you will, was logarithmic equations, and it said exponential equations. So I'm going to show you examples now of exponential equations and how we solve them. And sometimes we turn them into logs. Just like these log equations sometimes turn into exponentials. Now we've actually seen an example of this first one before. We were doing something different with it, but we solved it in much the same way. There's basically two types of problems for exponentials. There are problems where the bases can change to be identical, and there are problems where the bases can't change to be identical. So if you take a look at 16 and you take a look at 32, if I were to break 16 and 32 down into factors, 16 is like 4 times 4, 4 is 2 and 2, so 16 is 2 to the 4th. And if I were to do the same thing for 32, I have, 8 and 4, 4 is 2 and 2, and 8's actually 3 2's. So this is actually 2 to the 5th. Everybody with me? I can factor the base into something that has the bases matching. They both say 2 to a power. So over in my problem, I can rewrite them that way. This is 2 to the 4th to the negative x minus 4. And on this side, it's 2 to the 5th. Okay, on the last problem, once I got it to the point where it said logs, and I said, hey, look, they match. Now I can ignore them. That's what we get to do here too. Hey, look, the bases match. Now we can ignore them. So what do? Well, these two, we know they multiply, right? So we're going to write them down as multiplication pairs. This is 4 times negative x minus 4. And it's going to equal the other exponent, which is 5. Simplifying and solving, we have negative 4x minus 16 equals 5. I'll add my 16. So negative 4x is equal to 21. Dividing by negative 4. Again, you can leave it as negative 21 over 4. That's totally fine. If that bothers you, what's the decimal for that one? I didn't write this one down. I think I know what it is, but... Oh, good. That's what I was thinking. Very nice. Now, the problem was exponential, so it doesn't really matter whether it was positive or negative because exponentials don't have the same interior problem as logs. What was your question, Devin? I'm sorry.
What happens to the t?
Nothing happens to it. What we're doing is we're comparing. It's kind of like saying over here what happened to the log. Because they matched, they can be ignored because the only way the whole equation is going to be equal is if the exponents are equal. On this one, the only way the equation is going to be equal is if the insides of the logs are going to be equal. So it doesn't really go away. It just becomes irrelevant to finding the solution. Yeah. Okay, so one possibility is you get the bases to match, and you do that by factoring. Okay, so factoring is like what you've been doing factoring for a really long time with constants. You would factor. So this is the only example I have of one where they have the same base. I have 3 more examples, and they all have different bases because different bases are trickier to do. So let me show you what I mean. One side has a base of 7. The other side has a base of 2, and those numbers are both prime. But even if they weren't prime, and you tried to factor something at this point, if you have things that don't factor into the same bases, they'll be solved in this way. So what does it look like? Well, my goal is to get that y that's in the exponent to be down, right, to get it out of the exponent. And we do that with logs. That's actually where we began our whole log discussion was. What would we do if we needed to get this exponent to be not in the exponent location? And we introduced the idea of, notationally speaking, logs. So what we're going to do is you can use, and this is the most convenient, whichever one you like, either log or natural log, because you're going to use your calculator to solve this in the end anyway. So if it bothers you, if one of them bothers you, just use the other one. I'll use each of them as I'm working on these. I'm going to use log itself right now. So let's say we do log. And all I'm going to do is I'm going to put log on both sides. It's kind of like if you were trying to solve something and you took a square root of both sides. Okay? It's an operation. Log is an operation. So I'm logging both sides. That's not a real word. Don't repeat that, okay? But that's what I'm doing. I'm logging both sides. Well, why am I doing that? Well, because there was a cool property in the last section that we did that said if I have a log and I have an exponent, what can I do? How can I rewrite it? I can write it as a coefficient, which is kind of what my point was, right? I was trying to get that coefficient or that exponent out of the exponent spot. So this can actually come down. So now I have 8y log 7 equals log 2. Now here's the deal. Log 2 is a number. Log 7 is a number. They're ugly numbers. Your calculator can find them though, right? They're just numbers. So what would I have to do to solve here for y? I would subtract Macy if they were added, but they're not added. You would divide because they're multiplied. So right now there's an 8 being multiplied by the y, and there's a log 7 being multiplied by y. Are you guys with me? So I can actually divide by 8 and log 7. Here's the thing. Your calculator needs you to put the denominator in parentheses. Most of them do anyway. Otherwise, it will think divide by 8 and then multiply the answer to that by log 7. So you need to tell it that all of that's part of the denominator. So I would end up getting y equals, it is log 2 over 8 log 7. And we're going to round to the hundredths because that's what I said at the beginning. 0.0 what? Okay, and if I do hundredths, I've got 2 decimals, so it'd be 0.04. I think you rounded the 5 to get it to be 5, did you?
Well, mine says 0.0445. So
445. Like this.
yeah.
So when we round, we look at this one right here, and that number is a 4, so this
Oh, weird.
4 will
Sorry,
stay.
I was doing
Yeah. 0.04. Did anybody's calculator not give them 0.04? If so, we probably have a parenthesis and I'd like to handle it before we go on. Everybody's calculator is giving him the 0.04? Okay. But if it had to the nearest hundredths, then Keely, you'd be right, it'd be 0.045. Or to the nearest thousandths, I mean, which is some of them will say thousandths. Okay. Here's something interesting. One of them has a base of e and the other is a base of 6, right? Clearly the bases don't match. And I could actually use either natural logs or logs here, and they would work just fine. But it might be kind of nice to use natural log. Why? Because the base is e. Are you guys with me? It's actually a base e problem. So if I use a natural log, I am using a log with base e. So if you choose to use regular log, you'll get the same answer. It's not going to hurt anything at all. Your work will just look a little bit different here in a moment than mine. Okay, just like the previous problem, I've got the ability now to bring this exponent down, which is really the goal. Y minus 2, I have natural log of e equals the natural log of 6. This is a beautiful thing, because what's the natural log of e? 1. It's 1. So if you use log right here, you'll have to keep working with log e, and you'll have to move it to the other side and so forth. But if you use natural log, then the natural log of e is 1. So all I have is y minus 2 equals the natural log of 6. And what would I do? Add the 2, right. Now don't go tell me that that's the natural log of 8. That's not what it is. It is the natural log of 6 plus 2. And your calculator will do just fine. It might, depending on what your calculator does, put parentheses to just make sure that the 6 is the only thing in the parentheses if it is putting some parentheses on there. To the hundredths place, 2 decimals. What is this? 3.79. Okay, I have one more problem, and it is by far the most difficult we've done today. We're ending on a tough one. Can you tell why this one's tougher than the ones we've been doing, the last 2 problems in particular? Yeah, I've got the different bases, just like the last 2 problems, but both of those bases have exponents, and that is going to make the problem messier. Just is. Okay, the process works the same way, it's just the algebra solving it at the end that gets ugly. So let's take a look. You can use logs or natural logs, doesn't matter. Okay, so pick your favorite. I'll use natural logs on this one. And you're going to do the same thing like we did before, where you just put the natural log or the log on both sides. And again, the purpose for doing that really is because it allows us to take our exponents down as coefficients. So now this is 9x natural log 8 equals negative x minus 6 natural log 5. Okay, is everybody good with that? Notice I put parentheses around the negative x minus 6. Did you notice that? Because all of that's actually multiplied by natural log of 5, right? You all right? It's okay. So, I need to solve for x. The problem is that I have x on both sides of the equation, right? And I need to get them on one side of the equation. So I need to move something with addition and subtraction eventually, but I can't right now, because right over here, I need to actually distribute first. So we're going to do that. I have 9x natural log 8 equals negative x natural log 5 minus 6 natural log 5. Now I can actually move the x's to being on the same side. And I'm tempted to go to the left-hand side. I like to move things to the left when I can. It also makes it positive in this case. So we can add the x ln 5 to the left. So I'm going to write this out. This is 9x ln 8 plus x ln 5 equals negative 6 ln 5. So success, we've got the x's on the same side, woohoo! But there's still 2 of them, right? That's a problem. But it's not hard to solve it. Because there's an x in both parts, we can factor it out in front, just like when we did factoring of polynomials. So we can pull the x out. It makes 9 natural log 8 plus natural log 5 equals negative 6 natural log 5. At this point, please recognize this is a number, right? And this is also a number, right? So how about we get some decimals for them so we don't have to keep moving around logs, since they are really numbers that I can approximate. And we'll keep, because we're going to divide them here in a minute, let's go ahead and keep maybe 4 decimals, and then we'll get the answer to 2 decimals at the end. But here's an x. What is 9 natural log 8 plus natural log 5? And I don't have that part written down. I did mine a little differently. Sorry, one more time, Keely.
20.3244.
Okay, cool. And then what is negative 6 natural log 5? Okay, a little louder, McKaylee.
I got negative 9.66.
Can you give me 4 decimals? 6566. Okay, cool. All right, so what would I do then to solve this problem? I would divide by the 20.3244. And my answer to that division we will write with 2 decimals because I'm done at that point. So what is negative 9.6566 divided by 20.3244?
Negative 0.46.
46?
48, sorry.
48. Okay, 48 is what I had written down too. And I did mine in a slightly different way, so that's good news. That's good news. Okay, and again, this wasn't a log problem to start with, so I don't have to worry about going back and making sure that that's an okay value. It only is a log issue that we had for our domain values from before.